Hello and welcome everyone. My name is Håkan Råberg and this talk is about light and adaptive indexing for immutable databases. And I will start with the immutable part and then work backwards towards the indexing. I work for a company called JUXT, which is a software engineering firm based in the UK. But first, let's go back to 1980, where at this workshop in Monterey, south of San Francisco, George Copeland did present a paper called What If Mass Storage Were Free? This is a nice short paper which investigates this assumption would mean for database systems. I want to focus on its two main points. First point is deletion considered harmful. This is what I would call the functional programming or engineering argument for immutability. That is, improvements, functionality, simplicity, etc. can be achieved in a database system by eliminating the deletion mechanism. This is a compelling argument, but it's mainly about internal benefit for us as engineers, and it's not enough on its own. The second point is the importance of access to past states. In human memory, no deletion mechanism exists. People do not delete. Deletion was invented to reuse expensive computer storage. We could call this the memory or history argument for immutability, and it's a much more important one as it's the external user-facing benefit. Because our trade is something we initially took for granted, access to history for this ability to reuse storage. He goes on giving various examples of this, why this is important, like trend analysis, auditing, and historical information, etc. Nothing of this has actually changed in the past 40 years since this paper was published, which shouldn't surprise us, as the need for this predates computers by thousands of years. Copeland tried to sketch something based on the kind of technology he has available to himself in the early 80s, which involves using write once, read many optical disks, which is something which makes me think about 1986. So I attended this radio and television fair, Vision 86, with my mother in Stockholm. I was 9 years old at the time, and I have a strong memory of this being an awesome event, but I actually don't remember anything from the event itself, beyond the fact it was the first time in my life I saw a CD. This would be an audio CD, CD-ROMs were kind of coming a little bit afterwards. CD, of course, also form optical discs, like the ones Copeland discusses. CDs are defined by the so-called rainbow books, where the red book is audio, yellow is CD-ROM, and orange is writable CDs, etc. Now, 700 megabytes of storage was just an immense amount of data back then, right? There were several orders of magnitude in the kind of data I was kind of seeing every day. Of course, I was 9, right? And I do remember thinking a few years later, I may be able to kind of fill up a few CDs in my entire life, like that kind of be the kind of amount of storage I would ever need. This was later proven wrong. Yeah, now in 1986, I would have been using the Commodore 64. I was using tapes. Now a 60-minute tape on the Commodore 64 can store on each 30-minute side around 100 kilobytes of data, right? So this is the kind of storage I was working with at the time, right? So I found this book, Filing Systems for Databases, and database for the Commodore 64, while looking for articles in old magazines which could kind of inform my memory about this Vision 86 event, which I'd kind of totally forgotten. Like this book gets quite a good review in the magazine. Like it has a really good chapter about sorting apparently. I haven't read this book myself. Like I'm not sure if it's easy to find a copy of it today. But they give it some criticism for actually not bringing up secondary indexes and only focus on primary key lookups. So we'll see. I'm going to try to avoid this mistake in my own talk. Like I haven't read this book, as I said, but it does not discuss immutable databases, I'm prepared to guess. Yes, so later in the 80s, I was owning an Amiga, and storage was still neither mass nor free. Like a considerable amount of a limited amount of money was spent on buying floppy disks. And 20 megabyte, not gigabyte, right? Hard drive cost more than the actual computer you own, right? So this was like simply beyond my means. I could never ever buy like a hard drive at this point, right? Like I would later get one, like early 90s sometime potentially. Now, as Copeland pointed out, I didn't actually want to delete my diskettes. Despite the cost and limitations of these floppy disks, right? The actual work involved to getting this data onto those disks in the first place was just too big. So essentially, people do not delete, and I didn't want to either, despite this. Yes, so the 80s was simply a time of physically moving media around, right? You were carrying disks, you're kind of going off to the other side of town with the metro, kind of buying disks from someone you kind of got in contact with from some ad in a newspaper. You're kind of sending disks to the other side of the country, hoping they will come back with something stuff on it. You kind of send cash usually with them as well. This is kind of like the swapping scene, essentially. This was pirated stuff. Yeah, so even back then, my inclination was towards immutability. Like once you got a hold of something, you did not want to get rid of it. You bought more disks, essentially. So on that note, let's move forward, fast forward to today, 2022. Yes, so towards immutability. So we are building an immutable database as our company, JUXT. It's called XDB. This talk is not about XDB, but I will have to mention a few things because it's going to be easy for me to explain and inform some of my thinking. So most of the stuff I'm actually going to talk about is based on academic papers. So it's like this treasure trove of things you want to kind of dig into and read and kind of learn from. So there's going to be a little bit of a meta element of that as well, like how do you actually start doing this? Like we're a small team, we don't have any PhDs, we have like lots of good engineers, but this is not our natural element, essentially. Yeah, so reference to all of these papers will be at the end, and I will post a link to the talk, the slides, at the end of the talk. So if you're interested in any of this, like there are many ways you can enter this space, right, and become interesting. So yeah, let's have a look. So when you think about immutability in the actual industry and today, you may start thinking about analytics, or at least I think about analytics, because this space which potentially moves a little bit faster than transaction systems, because you can innovate a little bit more here, right? Like you're not as dependent on having like low latency transactions or like full-on transactional acid correctness, like so you can build a lot of systems, and people do. It's like a bewildering space. You have everything like, you know, functional programming inspired systems like MapReduce. You have data pipelines like Spark. You have data lakes and table formats to actually manage these data lakes. Like there's just an immense amount of stuff. You have the old data warehousing stuff where you kind of append-only fact tables which you kind of introduce. So there's an element of immutability here, right? And because this data often tends to grow, there's also a connection to the concept of separating storage or compute, which is going to be a key theme in this talk. Now, an attempt to kind of like, so initially, right, we didn't necessarily need to split this up, but it's like by historical extent, the industry has kind of split in several different directions. So there is this concept of hybrid analytical transactional processing, HTAP, which is an idea of trying to bring this stuff together again. Now, there will always be needs for like high performance transaction systems, very large data like analytic systems, but maybe for the common case, we could move back to like an HTAP world for some use cases, right? So, separating storage or compute. So this line here, right, this is separation. So this is a common concept. You will already have recognized this, you probably already maybe heard of it or know it, but even if you think about your normal applications, you will usually have like a stateless thing, which is your service, and then you have the storage somewhere else. But your storage is someone else's service, right? For example, it's a database, or in this case, if you're building a database, the storage may be the object store, like S3. S3 itself will recursively also be separated in this case, like there will be some services and there will be some advanced thing. I actually don't know how it works, but we'll actually separate out the data into various real-world disks, right? Yeah, so you have a granularity like stair here essentially, right? Like you have small things on the top, like the CPU cache, of course, much smaller. Then you have RAM, you have the local disk, which is only used as a cache in this context. Like you don't really want to store anything, but you're allowed to store, and this is especially easier when you're using immutable data. Like so you essentially, no one will going to change your files underneath you, right? Because you can just, as soon as you've seen it, you can cache it. The distributed cache is totally optional, but it's there for you to kind of avoid touching the object store in the first place. So there are several systems for using this, both the kind of like analytics systems and more modern kind of like HTAP attempts or like different strategies that are trying to do this. So, and we are also building one which kind of uses this rough architecture. Now, here's an early paper from trying to build, so like the idea of separating storage compute is not new, right? But trying to actually build a database in this matter is, yeah, while not new, it's not like super recent. You don't have many of them actually, maybe like, at least on the transactional side, like in production ready. I'm not saying there are none, right? But like, because it's almost impossible to know exactly what exists out there. But anyway, this paper is from 2008, building a database on S3. And this is actually not about immutability. They're trying to essentially just replace the page buffer in a normal database with S3. And then this, instead of writing to local disk, they write them onto S3. And this kind of works. But as you can see, you're going to introduce some kind of coordination between these nodes. In the paper, you use SQS to actually coordinate between the nodes to figure out who is allowed to write to which page when. So, but anyway, it's a cool like proof of concept idea. Right? Another related concept, which is like not directly related to separate storage and compute, but kind of related to analytics and this entire idea that some of the innovations coming from the analytical side and now kind of moving in towards the transactional side is the composition storage model, which is another Copeland paper from '85. So at this point in time, Copeland was working on like a Smalltalk object database called stone, I think. It later became like a Java database and still exists potentially. So I actually have no idea how this design relates to the object store stuff, but like in object database, that's not object store in the S3 sense. Yeah. So these column stores, this is what we today call column stores, right? Like, so it's like, it's an early paper, he doesn't use the term column stores, but we tend to refer to them as column stores today. There's also a related concept called wild column stores, like Cassandra and stuff, but it's not really the same thing. This is all about like an efficient access to arrays. It's quite, in a way, the basic idea is quite simple. You're building things with mechanical sympathy, which works well on kind of like sequential access to data, which also is kind of a little bit related to coming back to the kind of immutable data, because you kind of work with append-only data mostly when you write. So you prefer sequential reads, sequential writes. Of course, you still have random access at times. So yes, so our system is an H-step column store. So this is how this is somewhat related to what I want to talk about. So here is Copeland's paper from '85. So on the left-hand side here, you have what we would traditionally call a row store. Like, so this would be a normal OLTP, Postgres kind of database, where the rows are kind of like the columns of the rows are clustered together. So if you see on the left-hand side, you see something called a surrogate. So this is usually called like a tuple identifier or row identifier or an object identifier, something which identifies the row itself. In this world, this is still kind of like hanging together. Copeland refers to this as the n-array storage model. So on the right-hand side, this is Copeland's variant of the columns. In modern column stores, you don't always have the surrogate key, but you use the surrogate column. So it's not just a value column, right? You have two columns per column, and one of them is a surrogate. Sometimes surrogates doesn't exist because of the index itself. But this is what you use to kind of correlate the different columns together. In some systems, you wouldn't necessarily have all of the values for all columns. So you can potentially, a row can have different columns from another row. So that's why you need these kind of surrogate keys to kind of correlate them back up together. Now, briefly, our architecture. So on the left-hand side, we have SQL clients. In the middle is the compute. This is our actual system, right? So on top, we have SQL frontend, SQL planner. We use Arrow for almost everything because we are kind of a columnar database. The local object cache is going to be more interesting for this talk. And then we are about temporal, because once you're in the kind of immutable space, it's relatively easy to kind of patch on by temporality on top of that. It's a different feature set, but immutability is the foundation to do that. We're not going to talk about temporality in this talk, because it's like its entire own topic. On the right-hand side, we have a write-ahead log, which is like where you post the data in, and that's going to asynchronously be processed on the nodes, and then every now and then, right? So this is kind of like a gap or a buffer problem, right? That you cannot write every transaction into the object store directly, or you could and then try to kind of merge them together, but that introduces a lot of latency and slowness. So you want to kind of buffer them up. But the durability in our system comes from actually when it hits the log itself, then it's kind of like it's durable. Eventually going to be reduced into some kind of object when you get enough of rows or like data, so you can actually write them down to the object store. This talk is about this piece, right? The actual indexing, which is what happens when you need to efficiently navigate the object store. Like, so we're not going to talk about columnar execution. We're not going to talk about temporality or SQL, even though there's interesting topics. We're also not going to talk about transactionality, which is somewhat related because it's some overlap, like when and how can you read things. Like one very nice thing about immutability, now segueing very briefly into this topic, is that you can always take a watermark or kind of read from, like no one's going to change this or come in, so you don't really need like any locks to do reads. Okay, so what is the problem we're trying to solve here, right? Like what's the real problem which motivates this talk in the first place? So I call it the latency problem. There may be like a proper academic term for this, right? But it's like, yeah, shared disk strikes back. We have had decades of shared nothing architecture where like compute and storage is usually coupled, which like, and then you enter into this kind of sharding and partitioning problems. And this is kind of like the mainstream way of doing things, I would say. Like, but you're starting seeing this more and more, and instead it's kind of coming a little bit from the analytical side first, because you don't have the same transactional problems. I'm not saying this will come all over the place anytime soon, but you can find a lot of papers about this. Yeah, so this enables Copeland's vision, right? So of course, it's not free mass storage, right? Like it never gets fundamentally free, but it's much, much cheaper than it could have been if you didn't use something like an object store. Yeah, the data still needs to be found and navigated, and this is like one of the crux of the problems, right? This is kind of like part of the indexing problem. So the index problem obviously have two sides. One is the kind of finding and navigating the data. The other is that, like, because this introduced latency and request costs, you want to minimize actually accessing the data in the first place. So it's kind of like two sides almost of the same coin that you need to solve. Yes, so what is the solution? This is kind of like my sketch solution. We're going to go into the details of this through the talk, right? And a lot of this is actually based on ideas from academia, but I have to kind of adapt it a little bit to our real engineering context, right? So the solution is indexing and caching of indexes. So indexing and caching of indexes. So like you need to kind of, this is the basic, right? You need to create the right index and you need to cache everything, and you want to avoid ever falling off this cliff. Occasionally you will fall off the cliff, but for transactional processing that may not even be acceptable considering which circumstances you're in, right? So what I call light index or immutable index stored in storage, they're not necessarily light in the sense that they are small. They are light in the sense that they are simple to build and they're very small compared to the data they index. You want to kind of like a magnitude, kind of like fan out from these things, right? Like the adaptive indexing are totally different, right? They're running on the compute nodes and they can use more dynamic, like the specific techniques which are tuned to a specific workload at time. They're totally transient to disappear. There is a simplification here because there actually is a connection between these two, because you can use the adaptive indexing to guide what you actually want to build a real kind of index for in the first place. So we need to turn to academia for inspiration, or at least I need to turn for academia for inspiration. So now we're going to look a little bit what we can find there. Yeah, so this is kind of like a meta slide, but I think this is kind of interesting itself because like it's not about reading one paper, right? Like you need to go through a lot of papers and also quickly kind of ignore most of the stuff you kind of find and actually find the things that are interesting to your problem, because you are not there necessarily to kind of like, oh, I'm gonna, you know, write this thesis on this. Like I want to get some techniques that other people have thought about and be able to leverage them in my engineering setting, right? So what I would say is like you skim the abstract and you look for interesting pictures. This may sound simplistic, right? But actually when you're going to read a lot of papers, you're not going to read them, but you're going to look at a lot of papers, you want to find like, is this even interesting to me? Like, so you want to definitely resist the temptation to understand each paper. I think this is quite common. Someone give you a paper and you can try to read it and try to understand it. There's a time and place for this, but it's usually not when you're trying to find solutions to your problem, right? So you want to find a pragmatic approach via the references. I would say you usually find like there's some kind of like groundbreaking paper which may not even use the terminology, like the composition paper is a good example of that, right? But then later you have good papers that actually kind of like make it a bit more mainstream, you can understand it. But between this you have lots of incremental papers, just an increment on an increment, which you kind of like, these are usually the first you find, and it's like what you need to work yourself backwards to something that actually works for you. Another very important thing is you can use this to invalidate your ideas. We can spend forever trying to build things. Of course, you can't 100% trust what the papers say, but you can at least get a feeling like this approach probably not worth spending months building and then realize it actually won't work, right? So in the end, like if you want to understand one paper, of course we have papers we love. This is good, right? It's a good way to get started reading some academic papers, but it's not really the way to kind of like, this is going to be like very established papers, which probably also going to be covered in textbooks and stuff. But it's a good way to get started, but it's not going to give you this like current, like what's happening in academia. So archive.org is kind of like a fire hose. You can get like, so I kind of follow like, 7 topics maybe which are related to what I'm working on, and you get like loads of paper per day, and you need to skip most of them. Like, so, and then once you find something there which seems somewhat interesting, you can use something like semanticscholar.org to actually navigate a graph of papers. So this like, we could talk a lot about this, but sadly I don't have time, but there are also many other kind of sites like this and lots of paywalls and things in this world. But again, it's about reading papers, not a single paper, right? Like this is the problem when I have a specific engineering problem, I want to gain some understanding from academia, right? Okay, so a little subfield which is kind of up and coming right now is this thing called machine learning for database system. So I'm going to admit, we're not going to talk about any advanced machine learning, so it's going to be kind of underwhelming potentially if you come here to hear something really, really heavy. There is really like funky stuff going on in this field, but I'm kind of mainly looking for more pragmatic stuff. It's usually not that advanced when you start looking into it. So you have a few different kind of research groups I want to highlight. We have kind of like the self-driving databases group, or like thing from Carnegie Mellon, which Andy Pavlo, and then you have like, I would also strongly recommend, a little bit related to the previous slide about finding papers, right? Andy Pavlo has these courses on CMU, which are really, really good if you want to get into like reading some papers, understanding database systems. This has been like, I would not have been able to get halfway without getting that kind of basis, because like when you start reading random papers, you cannot really just do that. You need to have some minimal foundation to know what you're actually going to kind of connect it back to. You have adaptive indexing by Stratos Idros at Harvard. this is like this predates the machine learning thing, so I'm not even sure if you would call it machine learning, but it's still part of this kind of entire adaptive learning, doing funky stuff based on your data, right? You have instance optimized systems from MIT. There's also the group that does the learned indexing. We're going to get that next. So one kind of rough idea is you want to learn from the data, like both the kind of actual store data and also from the kind of metrics and other things. Like there are really interesting stuff around kind of workload prediction and things like that. I'm not going to talk about that because I don't really know much about it, but I think that's going to be paramount to actually make some of this stuff work for real, as I said, because you don't really want to fall off that cliff hitting the store more than necessary, even if that's even acceptable. So kind of if you want to kind of a little bit like tongue-in-cheek, it's kind of like taking DBA out of the loop. You shouldn't, if the computer can figure out which indexes need to exist and how they should look and what data is accessed, you can use stuff like this to actually go there. But of course, this idea is not new. Like, so this is actually under Pavlov's advisor's advisor, so he mentions it in blog posts, so I kind of took it from there. It's like index selection in self-adaptive database management systems. So this is paper from 76, right? So you, like there's generally really no new ideas, right? They are just rehashed in various ways. But this, honestly, is like a slightly different approach, but it's quite an interesting paper. So anyway, let's go into learned indexing itself. So I'm going to just use one example of learned indexes, because like there are loads of different papers up. So I'm going to become more concrete to talk about this one, which is called radix spline. So this is not the first one, but it's a kind of simple, which shows some of the ideas. So it's a single pass index, which means that it's actually kind of like you don't need to retrain or like go through the data many times. You can just swift through data once. It's by Kipf from 2020, and it estimates the cumulative distribution function. You could say, for simplicity, that this is just a model which maps from keys to a position. So you have a spline mapping from key to position, which is what this model builds, and then on top of that, you add a radix layer. So I'm going to show you how this looks, but first let's just show you the general idea of learning. So this comes from the case for learned index structures by Kraska 2018 et al. So this, like on the left-hand side, a traditional B-tree index, which kind of like it's also kind of a model. You get like, okay, here's a position, which you have kind of coded up through your internal nodes, and then you kind of, somewhere in this page is my data going to sit. The general idea of learned indexes is that you kind of like, oh, I have some kind of more advanced, or kind of, in this case, a neural network. As I said, we're not going to talk about neural network, but just some kind of model which then can try to estimate within this error bound. And this error bound is very important because otherwise you don't get the guarantees you need to actually be able to use these things in reality. But so the point, right, is that these are quite light and small because you kind of condense the data, like the actual data that needs to be stored for the indexes is quite small compared to the data itself. So let's look at radix spline. So here, first, x-axis, you have keys, y-axis, you have indexes. Here's an unsorted column. So let's just start by sorting it. So this, in a way, you actually not, by already you can see this not single pass in that sense. It kind of usually assumes a sorted because you cannot really learn anything from the random data, right? But let's accept that. We have sorted this thing. We're now going to build some splines. So these spline points, these are going to be like a magnitude smaller in amount, and actually there are 1 million data points in the green CDF line there, right? You may have 1,000 or 10,000 actual spline points on which you can dig out. And this, again, a bit underwhelming. This is the machine learning step, right? How to find. It's essentially just a spline estimation curve fitting algorithm. So on top of this, they put a radix table. So this, in this case, they're using 3-bit radix, which means that you have 3 bits, 8 buckets. And what they just do is to look at each spline point, and every time the first 3 bits change, they put it like, it's almost like a skip list. You put kind of like a shortcut, so you can go directly into this spline point. So you never need to look at the entire index. Yeah. So here an example of a query is 47183 in decimal. It's a long number in binary. I'm not going to read it, but it starts with 101, which is 5 in decimal. So this means that you can directly look between 5 and 6, and you will have a few spline points there, which you can actually then look. So you can skip most of the spline. Once you just looked at these, you have 3 essential points you can look at. The last point is not going to be, because something starting with 5 will never start with 6. So you can look at 2 other points. Once you found a point which is lower than the thing you're looking for, you find the highest point which is lower than the thing you're looking for, right? And then you do a linear interpolation there. So how do you build this spline? So here's another paper. It's a bit earlier from 2008, smooth interpolating histograms with error guarantees by Neumann and Michel. So you see, there's not a lot of data. This thing that actually fits the spline. So I'm going to try to walk this through. It's not going to be necessarily like super clear, but you can go to paper, you can look and read and understand it. But I've taken the diagram and breaking it down into the parts. So this, all of the white points are points which are going to assign on these two lines in the algorithm, right? Like, so B is the new base point. So what a base point means is that like so this cone you see here, this red thing, this is like the arrow bound, which is the allowed arrow bound. This is going to shrink as you walk your data. You're going to shrink this cone down. And essentially once something ends up outside the cone, you need to introduce a spline point. So at this point, when we enter this algorithm, you will already introduce the spline point B. So C is the current point. And you can see here, U is C plus error, L is C minus error. And these are these error bounds which I talked about earlier. So this is going to bring the initial kind of like cone for step 1. Then we get a new point, so we move. So now forward, this green line means that this point is actually sitting within the arrow bound, which means like this, you don't need to introduce new spline point. This is fine, right? Like we can keep going. But now you're going to look at the arrow bound. So now we're looking at the new potential upper bound. This red dotted line here means that this is actually wider arrow bound, which means that I don't press any need. Like I'm not allowed to widen the bound. I'm only allowed to kind of tighten the bound. But on the L side, you see that the new L is much closer than the old L, which means that the cone actually gets tightened. So it keeps doing this until you eventually something ends up outside the cone, and then you restart the process introducing a spline point. Yeah, and this is how the actual diagram looks in the paper. I'm just going to quickly mention different index, which is called a PDM index, which is built in the same way, but you don't add the radix later. So in this radix spline, you build one spline, add the radix later on top. This is that builds a spline on top of a spline on top of a spline. So this is a different approach, but use kind of the same building blocks. They use a slightly different spline algorithm, but the concepts are kind of the same. I'm also going to mention a kind of slightly different thing while on the topic. Is like, because when you're using immutable data, you usually don't want to kind of rewrite or resort the base data. So the base data have a tendency to maybe be unsorted. So in this example, this learned secondary index structures paper, also by Kip and the MIT group, you'll see this is just for show, right? Like this is how it looks when it would have been sorted. But that's not what you store. You store this permutation index. This is, of course, not a new advanced concept, but it's a very useful trick. So a lot of the stuff is like combining quite easy to use things together and actually get the results you want. In this paper, they also have some hash bits to be able to avoid looking at the base data, because obviously like when you go into the base data, you're going to get some random access, which is not going to be as good as data that have been sorted in the first place. But that's kind of a different thing. Anyway, we move on to adaptive indexing. So this is like a highly influential paper by Idros from 2007. Again, it kind of predates this kind of machine learning thing. Idros and his group has some more modern, interesting, funky stuff, but kind of genetically breeding data structure and stuff like that, and figure out which data structure are the perfect ones for your thing, and they build it down as a kind of like the kind of first principles. But we're going to focus on this much more simpler thing, which like what it really just does, it incrementally sorts a column. So you will have an unsorted column, and then as the queries come in, you will do like one round of quick sort, called the quick select, and then you just basically sort as much you need, but not more. So this sounds good, but it requires tracking the piece boundaries. So this is like, often when you read these papers, like, okay, how do they actually do that? But actually you need an other data structure to figure out. So I'm going to show you how this looks. And it has some drawbacks. We're going to not go into that right now. There are many follow-up papers, and some of them are linked to in my references. Yeah, so here we have an unsorted column, column A. In comes a query, right? Like it's larger than 10, less than 14. So what it does, and this is the cracking, right? Like if you look at like between 10, like it moves everything below 10 into the first piece, and everything above 14 in the third piece, and then in the second piece, that's going to be your data you're looking for, right? So this approach allows you to avoid sorting the entire column. You can potentially ask yourself, when is it worth actually trying to avoid this? And this is always something one would have to kind of look at more closely. It keeps going and it keeps building more and more pieces. Now you can see here on the right-hand side that this actually will eventually become a problem, this amount of pieces, and you need to track them. So eventually to make this converge, either by just, I'm not going to sort below a specific size, or I'm just going to do the sort once I reach a specific size, so you don't have to track too many pieces. There are many variants in this paper, so it's quite interesting. There are also multi-dimensional versions. Yeah, so the final algorithm I'm going to talk about in this section is instance optimized system. I'm going to go over this very quickly because this is a vision paper by Madden from 2022. I discovered this paper while I was researching for this talk. I somehow missed this, came out earlier this year. This embrace separation store compute. The other papers, they are more like low-level data structure stuff, right, and kind of building small indexes. Like this is like more strategic, like building on a system level. And it aims to automatically create and modify indexes, and the goal is to minimize object access. So this is quite close to the stuff I come looking for. So this is a very interesting approach, or like to me it's quite interesting what they're going to come up with. So they apparently going to open source some stuff, but I haven't seen that happening yet. So here we have a classic separation storage compute diagram. On top they have some compute nodes, and they're kind of more or less independent. In the bottom you have the cloud storage, where these kind of what they call these data containers sit, and they're also kind of immutable, and they kind of build up depending on what's happening in the system. They also have this concept of in-memory containers, which are kind of a little bit like that adaptive index. It's not directly, they don't talk about like that. They refer to the cracking paper, but I see it like a little bit like you can do slightly different things on the compute node than the things you actually want to store in object store. Yeah, so this short and last section is about the engineering we are kind of embarking on, and we are kind of been doing. Some of this exists, some of the stuff we're going to do now, right? So this is going to, in a way, regroup some of the stuff I've talked about so far, but more in kind of like the way I think about it and the way we kind of potentially going to approach about it. So index immutable data, right? Think make. Like you have like queries on one side, and you have immutable data on the other side. In the middle, you have derived index. They're only there to help you solve like the latest problem. You don't really care about them so much. Like you need to do some engineering to make this problem go away, but the point is not to build this more than it needs to be. So one needs to measure everything all the time and think about, does it actually pay its way? Do I need a neural network here or not, right? Yeah. So you need to navigate the storage by layers of indexes. And this is very important, right? Like initially, you want to have just a very small index that can tell you roughly what exists in the object store. And then based on that, based on the actual usage, you will then basically derive more and more advanced indexes as you go. So the goal again is to minimize latency. Yeah. So light indexes, these are for storage, as I mentioned. They're created on demand, and they will be created in the background. These are not happening during the query. They will be happening based on what queries and what activities have been going on. They are idempotent, they are immutable, and they're shared. So that's kind of like a lot of the immutability goodness here, right? The data skipping is absolute key, and this is what I mentioned in the previous slide. Like you need to have some small metadata like min, max, bloom filter and stuff to even be able to call, I don't want to even look at most of the object store most of the time, right? Like your data will come in clustered based on insertion time in an append-only system, which is often not the way you want your data to sit. So for example, in Copeland's paper, he suggested you would store every column in both a sorted and then kind of like non-sorted version, like which is on append order. Like this is not necessarily feasible, like when you get enough data, right, and it's going to sit somewhere else, but you can kind of drag it towards that direction depending on what's actually happening. Yes, so adaptive indexing for compute. So these are dynamic in RAM, as I mentioned. These could be things like tracking, and there are other similar approaches. They are adapted by workload. So this, in a way, like they are kind of the seed to these other things. This is like where the first information into your system comes in. So you can go, oh, some people are interested in this data. This is going to potentially be useful to me, right? Like they're local and they're transient. Though you could be using them also literally, like once you've sorted the entire column, you could potentially use some of that to then build a spline on top of that, right? Because of this, you also run into concurrent modifications. You don't have all of that kind of like immutability good stuff, right? Because this is going to be happening potentially on the same box, and there are various ways you obviously can engineer around that, but you cannot ignore it. So, wrapping up, some outlook, right? Like one thing we're really using learning is for at the moment is multidimensional links, which I haven't talked about, which we use for bitemporal links. So this is a good paper called Learning Multidimensional Indexes, which also in the reference, right, which builds some kind of like learned grid file funkiness on top of like multidimensional data. So I think learned index has a lot of potential in the multidimensional space, even if it may feel a little bit like, oh, do I really need this for the one-dimensional space? And this multidimensional space is not just about multidimensional data. It could be like correlations between different things you can see in your data or your queries. So succinct data searcher has nothing to do with learned index, but they are like small for different reasons. So they are kind of like different approaches to kind of compress the data down, but not compress that kind of like G-zipping it, but like, you know, making it very small while still accessing it using very funky bit techniques, right? So they are not necessarily very fast to access, but they can become very small, so they allow you to achieve some stuff which are essentially almost impossible because you can keep a lot more data in RAM. then as I said, workload prediction is going to be kind of a key to actually make this feasible in practice, because once the data become big and you don't know, you need to start kind of pulling it more and more from the object store, it would be good to somehow figure out. And there are all kinds of things, from very simple things, right? You know, like I'm just going to pull in things which are reasonably used, like people like this object, also like this object and stuff like that. Or like funky machine learning stuff. But of course, all the machine learning stuff requires to have enough data. And this data, also, that is not like the data itself, but the kind of metric data, so you can actually learn something from it. So, summary, index on demand, think, make, Copeland, people do not delete, separation of storage compute, like kind of orthogonal to many things I talk about, but it's a very important concept, right? And academics inspiration, not gospel, right? If you want to learn a lot of good stuff from it, and it's like, I think to build the kind of system we're building, it's almost impossible or foolish to ignore it, but you can't really the point is not get sucked in all the way in, right? Yeah, so as I mentioned several times, I have a reference here, so we're going to post, we're going to show the link, and here is the link. So at this link, you can find the slides with your reference. If something of this was interesting to you, you can go here and actually have a deeper look. So on that note, thank you very much. So I guess I would have very short time for questions. Someone has a question, but yes? Yeah, okay. So the question is like, how does the spline mapping look in the radix?
Yeah, so I also, this is kind of what you were. Sorry, that was a bit of word vomit.
Yeah, well, I don't know. So the question is like, how is this related to log structure merge trees, more or less, right? So I think the short answer, I wouldn't say they're directly related. They're obviously similar ideas. You need to kind of map and track where the data sits, but you can then later apply log structure merge style techniques to merge several indexes and data together. But during this process, except that it maps to some data, I wouldn't personally say it has a direct connection to that. Yeah, so, okay, so the question is like, the light indexes are immutable. What happens when you mutate the data, essentially the underlying data you're indexing? Which actually then connects back a little bit to log structured merge tree thing, because one thing you can do is you can try to merge in new index based on the kind of new mutable data. So you don't try to mutate the data you actually currently have. There are also, I have not mentioned this in this talk, right? There are dynamic learned indexes, but they don't necessarily map well to this kind of immutable stored in an object store case, because like once you store it in an object store, you don't necessarily want to change that file, but you can then merge several files potentially to get a better like sorting thing happening on top. So, thank you. Sorry, the question is, are learned indexes taking something about size? Sorry, could you repeat the question?
Yeah, how much memory are learned indexes taking up? Is that a problem?
No, they're going to be magnitude smaller than the data you're indexing. This kind of, they're probably also going to be smaller. That's kind of one of the points of them, is that they're going to be smaller than, say, if you build like a tree structure yourself, which sits over, like they're also very good because you can map them out to columns directly, which are going to work like all other columns, but they happen to be indexes. So the general idea of them is that's part of the light thing. They're going to be very small, but again, I said the files don't need to be small, but they need to be very small compared to the data actually index. So this is one of the, I guess, one of the real motivations for the entire learned indexing thing. There's also talk about performance, but I haven't really touched upon that because it's like some kind of discussion like how fast are these really in practice. But I would mainly use them for this size. Okay. Okay, I think that's it. Thank you very much. Cheers.